Hello viewers, in the last session we learnt about removable singularities. Okay. So, couple of comments are in order. Firstly, that we can redefine the function. So, recall what a removable singularity is. It is such a singularity of a function of an function analytic function in the neighborhood that there is an extension of that function to an analytic function at the singularity itself. Okay. So, last time we showed a theorem that limit z goes to a. So, under the assumption that a is a removable singularity of a function f, if limit z goes to a, z minus a f of z is equal to 0. Okay. So, this is if and only if f has a removable singularity. At a. Okay. So, recall what that means. It means that there is an analytic extension of f at the point a. Okay. So, often we will whenever there is a removable singularity, we will say that we will remove the singularity at a for f. What that will mean is that we will consider the extended function. Okay. So, this kind of singularity is a fake singularity, because all that is lacking is information of the value of f at a. Okay. So, by the theorem that we proved last time, this is the theorem that we proved last time, briefly stating. Okay. So, what we have is that now in retrospect limit z goes to a, f of z exists. Okay. If f has a removable singularity at f, a removable singularity at a. Okay, I will use a shortcut at a. Sing means singularity. Okay. And then what we have is g of z is equal to f of z in a certain, okay, for z belongs to BAR, and it is equal to limit as z goes to a f of z if z is equal to a. Okay. So, that is your redefinition of f. Okay. So, this g is now analytic on, last time we proved that this is analytic on BAR. So, we will not exactly prove this, but in retrospect this exists. Okay. If and only if this limit exists. So, in retrospect we can define g of z to be this at z equals a, and so that g of z is going to be analytic on BAR. All right. So, so often we will, okay, often we will write this g, okay, as okay, or I will say that often we will write g of a as f of a, okay, and call g to be the function f with the singularity at a removed. Okay. So, we will say that the singularity at a has been removed, okay, of f has been removed, and the new function with f of a as g of a is the extended function. Okay. So, this is a piece of notation, if you will, or just language. Okay. So, next we will consider the other kind of singularities, namely poles. Okay. So, recall in the examples that I gave in the last session, there was a case where the modulus of the function in a small neighborhood around the singularity was tending to infinity as the z, the variable, approaches the singularity. Okay. So, this is a condition we will use to make a definition of a pole. Okay. So, let f be analytic on B prime A r. Okay. So, with limit z goes to A. So, it is analytic in a punctured neighborhood of A, but when you consider the limit as z goes to A of f of z, that is infinity. Okay. So, recall what that means. It means that the modulus of f is arbitrarily large in a small neighborhood. Okay. And it's large for every value of z in an arbitrarily small neighborhood. Okay. So, so what this means, recall limits as limits tending to infinity. Okay. What that means is that modulus of f of z is greater than. Okay. So, given m positive, okay, there exists a delta positive such that modulus of f of z is strictly greater than m for every z belongs to b prime of A delta. Okay. So, that is what this means. Okay. So, that is true for every m. So, given any m positive we can do this. So, that is your limit of f tending to infinity. Okay. So, by this very definition, picking m to be 1, let us say, we can say that there is a delta such that modulus of f is not 0 in that delta neighborhood of A. Okay. So, there exists a delta 1, okay, such that f is non-zero in B prime A delta 1. Simply picking m equals 1, for example, gives this delta 1. Okay. So, g of z defined as 1 by f of z. Let us notice the behavior of g, okay, is defined, at least is defined in B prime of A delta 1. Not only that, g is defined not only in B prime of A delta 1, but at A we will notice that g has a removable singularity. G defined this way has a removable singularity. Okay. So, g has the singularity of g. Okay, is defined in this, and I should also say and is analytic there in B prime A delta 1. Okay, because it is 1 by an analytic function, it is also analytic. Okay. So, the singularity of g at A is removable. That is because our favorite condition, limit z goes to A, z minus A times g of z. Let us notice what that is. That is equal to 0, because 1 by f of z is arbitrarily large in modulus, and f of z is arbitrarily large in modulus. So, 1 by f of z is very small in modulus, and so is the modulus of z minus a. So, in modulus z minus a times 1 by f of z tends to 0. So, in modulus, when some quantity tends to 0, you can conclude that the complex quantity itself tends to 0. Okay. So, so that is why limit z goes to A, z minus a g of z is 0. So, and also notice that since 1 by f of z itself tends to 0 in modulus, limit of g as z goes to A is actually equal to 0. Okay. So, we can redefine g at we can remove the singularity of g at A and define g of A to be 0. Okay. So, that is the value of the limit as z goes to A of g of z. Okay. So, so we can define. Okay. So, g has an analytic extension okay, with g of A is equal to 0. Okay. So, notice that I am not giving a new name to the analytic extension, I am not calling it some h, I am once again calling the analytic extension also as g, like like I said in the remark above. Okay. So, g has an analytic extension with g of a is equal to 0. Okay. That is since limit z goes to a g of z is equal to, I will write below, sorry, limit z goes to a g of z, g of z is equal to limit z goes to a 1 by f of z. Okay. And in modulus f of z is arbitrarily large in every neighborhood, I mean for every point in a neighborhood. Okay. So, this tends to 0 in modulus this quantity. So, this is equal to 0. Okay. So, we redefine that to be that, okay, and g is like that. So, now the extended function g, which we are still calling it g, okay, has a 0 at a. Okay. From the study of zeros of analytic function from earlier sessions, we know that it has to have the 0 of g at a has to have some order. Okay. So, by Taylor's theorem, okay, so by Taylor's theorem and its conclusions, by Taylor's theorem, okay, we can write g of z is equal to z minus a power k g 1 of z, okay, for every z belongs to B A. Okay. I will have to change this delta to some delta 2. Okay. So, because Taylor's theorem is a local theorem. Okay. So, the Taylor's expansion for g is an analytic function now. Taylor's expansion for g around A is valid in some delta 2 neighborhood of A, okay, and g has a 0 at A. So, we can pull out a factor z minus a power k from g, okay, with g 1 of A not equal to 0, okay, i.e. g has a 0 of order k at A. Okay, this is something we know from earlier. Okay. So, g 1 of A is non-zero. So, what we can do is we can now substitute what g of z is, okay, 1 by f of z is equal to z minus a power k g 1 of z for every z belongs to, notice I am deleting a itself because f has a singularity at A. Okay. So, in B prime of A delta 2, okay, and so g 1 of z now, okay, or I will say f of z times z minus a power k is equal to 1 by g 1 of z. Okay. Once again for every z belongs to B prime A delta 2. Okay. So, when I take the limit as z goes to A, I can take the limit of this quantity on the left hand side, that is equal to the limit as z goes to A 1 by g 1 of z. I probably should have remarked that with g 1 of A not equal to 0 and g 1 analytic on B A delta 2. Okay. So, I will need that because analyticity gives me continuity of g 1. So, this is equal to 1 by g 1 of A, and g 1 of A is non-zero. So, 1 by g 1 of A is also a non-zero complex number. So, the limit as z goes to A of f of z times z minus a power k is a non-zero quantity like this. Okay. So, that is the conclusion we draw. Okay. And notice that if alpha is greater than k, okay, then limit z goes to A f of z times z minus a power alpha is equal to limit z goes to A z minus a power alpha is greater than k. So, I can subtract a k and then limit z goes to A f of z times z minus a power k Okay. So, this quantity is a finite complex number and this quantity is 0. So, this is equal to 0. Also, if alpha is less than k, if alpha is strictly less than k, limit z goes to a f of z times z minus a power alpha, okay, can be written as limit as z goes to a, well, yeah, f of z times z minus a power k divided by z minus a power k minus alpha, which is positive, k minus alpha is positive. So, we have a term tending to a non-zero complex number in the numerator, okay, a finite complex number, and the denominator we know blows up in modulus. It has a very large modulus as z goes to a. So, this limit is equal to infinity. Okay. So, we have a tie at k. Okay. So, that is the situation, f of z times z minus a power alpha is non-zero at alpha equals k, okay, and for alpha less than k, it's the limit is infinity, and for alpha greater than k, we have limit is 0. Okay. So, this is the dividing point. So, I am looking at the limit as z goes to a of z minus a power alpha f of z for an integer alpha. As alpha varies, alpha is equal to k is the dividing point. At this point, this limit is non-zero, some finite complex number, okay, and for every alpha greater than k, this is 0, okay, this limit is 0, and then for every alpha less than k, this is infinity, this limit is infinity. Okay. So, there is a neat divide like that for this limit. So, what we will say is that we say, okay, in this case we say that f has a pole of order k at a. Okay. So, allow me to go back. So, if 1 by f of z has, I mean it has a removable singularity at a, and if 1 by f of z with its extension has a 0 of order k at a, then we say that f has a pole of order k at a. Okay. So, that's pole of order k. So, we have a order for a pole. Okay. Not only that, if the limit as z goes to a of z minus a power m, the condition goes other way around, power m of f of z is non-zero. If this happens, okay, then f will have a pole of order m at a. Okay. So, it is an if and only if condition. If this limit exists and is non-zero, then f will have a pole of order k or m, whatever that constant is at a. Okay. And if it has a pole of order k or m, then that limit accordingly will be non-zero. Okay. So, I am trying to show the other direction, I will give a heuristic proof. If limit z goes to a z minus a power m, f of z is non-zero, let us call it d, let some d not equal to 0. What I will show is f has a pole at a of order m. Okay. So, if that happens, then what happens to z minus a power m f of z in a neighborhood, in a small neighborhood of a, this is equal to d plus some w. Okay. W is a complex number with very small modulus, where for first I should write for z belongs to b prime a delta, okay, delta small, okay, and w has a small modulus. Okay. So, that is what limit means anyway. Okay. So, the modulus of z minus a power m f of z is between d plus epsilon is between the modulus of d plus epsilon and the modulus of d minus epsilon. Okay. And so, I can make this kind of statement. Okay. So, given an epsilon I can do that. So, I can make this statement. Okay. So, approximately the modulus of the right hand side is close to d, the modulus of d. Okay. So, in order to compensate, the modulus of the left hand side is growing smaller and smaller as z approaches a. So, the modulus of f has to compensate for the loss. Okay. So, the modulus of f has to go up. Okay. So, f of z is equal to d plus w by z minus a power m. Okay. So, this modulus stays closer to d, it is a finite quantity and this is becoming arbitrarily small. Okay. So, as limit as a tends z tends to a. Okay. So, the limit as z tends to a f of z has to be arbitrarily large. Okay. So, limit as z tends to a f of z is equal to limit as z tends to a d plus w. W is not a fixed quantity, it also varies as z tends to a, but it stays close to 0. Okay. So, z minus a power m. Okay. W, the limit of w really is 0. Okay. So, then we get this. Okay. So, so it is a heuristic proof, that is not really a proof. I mean, we can work out using the limit definition. Okay. So, this implies that f okay, f has a pole at a of order m. Okay. So, in conclusion, we have that limit z goes to a, z minus a power m or k, let me say k of f of z is non-zero if and only if f has a pole of order k at a. Okay. So, this is the conclusion. Okay. So, this is neat and useful. Okay. And then here is a quick example. So, let us consider z sin z, the function f equals z sin z. Okay. So, we know that z sin z has a simple zeros at k pi k not equal to 0. Okay. So, if we consider 1 by z sin z, okay, this has then has a pole of order 1. Okay. So, I am going in the opposite direction here. I am looking at the function g and looking then at the function f. So, 1 by z sin z has a pole of order 1 at any k pi, k not equal to 0. If k is equal to 0, you are looking at z equals 0, okay, then z is 0 and sin z is 0 as well. So, z sin z has a 0 of order 2 at z equals 0. That can also be inferred from the Taylor's expansion of sin z. This is equal to z times z minus z cube by 3 factorial plus z power 5 by 5 factorial, etc. That is the Taylor's expansion for sin z. This is equal to z squared minus z power 4 by 3 factorial, etc. So, you can factor out a z. I could have done that earlier, 1 minus, etc. So, z sin z has a 0 of order 2 at 0. Okay. So, then 1 by z sin z has a pole of order 2 at. So, that is a simple minded example of a pole. So, poles and zeros work in mutually opposite ways, like we have seen. If f has a pole, then 1 by f has a 0 at a point A. Okay. And then by that I mean it has a removable singularity, and once you remove the singularity there is a pole, there is a 0 of 1 by f. So, so what we can state is the following. Okay. So, here is a simple proposition, it is sort of the cancelling behavior of zeros and poles. Let f and g be analytic. I will say let f and I need different domains. So, I will say this differently, let f be analytic in BAR, okay, and let f have a 0 of order m at A. Okay. Let G be analytic in B prime AR, and let G have a pole of order n at A. Case 1, if m is greater than n, then f times g has a 0 of order m minus n at A. Case 2, if m is less than n, then f times g has a pole of order n minus m at A. Okay, so, they sort of cancel each other. So, if the pole's order is more, then pole dominates, and then there is a pole of order n minus m there. Okay. And then in the third case, if f m is equal to n, then f times g has a removable singularity, and it can be removed. Okay, removable singularity at A. So, these are the three cases. So, this is how the pole and 0 cancel each other. Okay. So, that is a simple proposition, and the proof is pretty straightforward using what we have already done. Okay. So, the viewer can provide the proof as an exercise, just to revisit all the facts that we have proved earlier. Okay. So, next I want to consider the other kind of singularities. Okay. So, before I do that, okay, let us consider the following, okay, to arrive at the other kind of singularities. What other behavior can f exhibit around a singularity? Okay. So, if f is analytic in B prime of A R, we have seen that f could actually be analytic in all of B A R. It can be extended to be an analytic function at A, which is the case when A is a removable singularity. Okay. And then f could have a pole at A, okay, in which case by definition limit z goes to A f of z is infinity, okay, and then we have seen its behavior. Now, we will consider what other behavior could it have at in the neighborhood of A. Let us consider the following two equations first, or limits first. Limit z goes to A modulus of z minus A power alpha times modulus of f of z is equal to 0, and limit z goes to A modulus of z minus A power alpha modulus of f of z is equal to infinity. Okay. At least in the case of a pole, we have seen that there was a dividing point, okay, which was the order of the pole. Okay. So, the value of alpha for which 1 held was any alpha less than k, greater than k, and the value of alpha for which this equation 2 held was anything less than k, where k is the order of that pole. Okay. So, we will we will examine these two more closely. Let us first suppose that suppose 1 holds for some alpha. So, given a function f, suppose 1 holds for some alpha. Okay, here we are working under the supposition that f is analytic in B prime A r for some r positive, okay. And suppose 1 holds for some alpha, okay. Then it holds because the limit is 0. So, you can jack up the power alpha as much as you wish, and the limit z goes to a of modulus of z minus a power alpha f of z in modulus will be equal to 0. Then it holds for any alpha greater than, okay, any real number, let us say, greater than alpha. That is the first statement. Okay. So, in particular, it holds for an integer m. Okay. So, we can pick an integer from numbers greater than alpha. Okay. So, for the time being I am assuming that 1 holds for some real number alpha. Okay. So, then it holds for an integer greater than that. Okay. So, limit z goes to a modulus of z minus a power m modulus of f of z is equal to 0. Okay. So, this implies that we can increase the power by 1 more z minus a power m plus 1 f of z, the limit of that as z goes to a is also 0. Okay. So, this implies that z minus a power m f of z, okay, has a removable singularity. Okay. Singularity at a. Okay. And since the limit of this function itself is 0 as z goes to a, we saw how to redefine functions at removable singularity. We will take the limit of that function as z goes to a, okay, and so this and z minus a power m f of z vanishes, i.e. is equal to 0. Okay, for considering the extended function, okay, is equal to 0 at a. Okay, so that is how we redefine. Okay. So, case 1, what could happen is f could be identically 0. If z minus a power m f of z is 0, one of the cases is that f could be identically 0. This is the uninteresting case, okay, in which case, okay, 1 holds. We consider 2 equations here. Okay. So, 1 holds for every alpha belongs to R. Okay. So, limit z goes to, we started by assuming that it holds for one particular alpha, okay, and what we have concluded is that z minus a power m f of z in modulus is equal to 0 in the limit. Okay. So, that will allow us to conclude in the case that f is identically 0, that alpha, I mean for any alpha that 1 holds. Okay. So, this is the uninteresting case, but what is more interesting is that if f is not identically 0, okay, then z minus a power m f of z, okay, we saw that it is already 0, the analytic extension of this is 0 at a. So, has a 0 of order, let us say k at a. This implies z minus a power m f of z is equal to z minus a power k times g of z, okay, and g of where g is analytic in BAR and g of A is non-zero. Okay, in some neighborhood of A, g is analytic and g of A is non-zero. Okay. So, by subtracting let h equals m minus k. Okay. So, we will make from this equation what we can do is we can write this as z minus a power h f of z is equal to g of z. Okay. So, now if alpha is greater than h, g is analytic. Okay. So, if alpha is greater than h, then limit z goes to a modulus of z minus a power alpha modulus of f of z is the modulus of g of z. Okay, is the limit as z goes to a modulus of z minus a raised to alpha minus h modulus of g of z. Okay. So, and that is equal to 0. Okay, because g is analytic at a, g has some limit g of a and then modulus of z minus a alpha minus h raised to alpha minus h is 0. Okay. And likewise, if alpha is strictly less than h, then limit z goes to a modulus of z minus a power alpha modulus of f of z is equal to limit z goes to a of modulus of g of z divided by modulus of z minus a power alpha minus or h minus alpha, no? And that is infinity. That limit is infinity. Okay. So, there is a divide, h is integer, notice h is h is an integer. So, in summary, we are able to conclude the following. So, if we assume that 1 holds under the supposition that this limit 1 holds, we are able to conclude that there is an integral point h on the real line. Okay. So, there is an integral point h on the real line such that for anything less than h 2 holds, okay, and then for anything greater than h 1 holds. Okay. So, there is an integral divide here. Okay. And then, so it is the first conclusion. Okay. And then likewise, if we assume that suppose 2 holds, one can likewise show, suppose 2 holds, one can likewise show that there is an integral divide on the real line for which 2 holds for every integer less, every number, a real number less than h, and 1 holds for every real number greater than h. Okay. So, I will show that. Okay. So, suppose 2 holds for some alpha, okay, then it holds for smaller alpha. That is because if things tend to infinity, okay, and you are decreasing the power of z minus a, okay. So, then the modulus is the modulus of f of z is competing with the modulus of z minus a power alpha and is anyway tending to infinity. Now, if you reduce the power of the quantity which becomes smaller, okay, the competition is more fierce in the sense that, or the competition is pretty much winning for f of z. So, it becomes even more in modulus. Okay. So, this limit for alpha less than that particular or quantity less than that particular alpha okay, still tends to infinity. Okay. So, then it holds for smaller alpha, that is easy, okay, and hence for some integer n less than alpha really. Okay. So, then once again we can do the same analysis, then z minus a power n f of z, similar analysis. Okay. So, has a pole of order L at. Okay. So, that is because the modulus of z minus a power n times modulus of f of z in limit is equal to infinity. Okay. And so, this function has a pole. Okay. Let us call the order to be L. Okay. So, then what we know is that letting h equals n plus L, like we have done for the other case. Okay. We find 1 holds if alpha is greater than h. Okay. So, I am writing the conclusion. It is easy to argue like we have done here. Okay. Like we have done all of here. Okay. So, 1 holds if alpha is greater than h, and 2 holds if alpha is less than h. Once again, here h is an integer. Notice h is defined to be n plus L. Okay. And once again, on the real line we have a divide at h. For alpha less than h, we have that 2 holds, and then alpha greater than h, 1 holds. Okay. So, there are, based on this analysis, there are, if we assume that 1 holds, then there is an integral divide on the real line, where 1 holds for values greater than that integer, and 2 holds for values less than that integer. Okay. And likewise, if we assume 2 holds for some alpha, the same kind of situation prevails. Okay. So, 1 and 2 are mutually related. The two kinds of limits that I stated earlier are related in this fashion. Okay. So, there are 3 cases based on this analysis. Case 1, condition 1 holds for all alpha belongs to R, i.e., okay, f is identically 0. Okay, that could be a case if f is analytic in a deleted neighborhood of, or there is an integer. The second case is there is an integer, that is with the suppositions. Okay. So, there is an integral divide. Okay. So, there is an integer h such that 1 holds for condition 1 holds for any alpha greater than h, and condition 2 holds for alpha less than h, for any alpha less than h. Okay. And then there is a case 3. We saw that if 1 holds, 2 should hold, and if 2 holds, 1 should hold. Okay. Unless there is case 1 where 1 holds for everything. Okay. So, case 3 is that neither 1 nor 2 holds. In the neighborhood of A. Okay. So, what that is telling is that neither does f tend to infinity in modulus near A, nor does f have a 0 of course at A, okay, nor does f have a removable singularity. Okay. And f of course, we are assuming is not identically 0, which is the uninteresting case. Okay. So, in this kind of scenario, what really one can say is that f is oscillating in its values in small neighborhoods around A. So, if you consider a small enough neighborhood, f could be possibly very large or possibly very small, but both the kind of behaviors should exist. Maybe it tends to one limit, and then there is a subsequence which we can consider in the neighborhood, which tends to some limit, and then there is another subsequence in the neighborhood which tends to yet another limit. Okay. So, that can be a possibility, that is the case 3. Okay. So, neither 1 nor 2 holds, which means so that is the behavior like I explained. Okay. But we can make a very strong statement in this direction, okay, of the behavior of f in case 3, okay, and that is the Casorati-Weierstrass theorem. So, I will first call case 3, we will give case 3 a name, an isolated singularity okay, of type 3, okay, of the type in case 3 is called an essential singularity. Okay. So, that is the definition of an essential singularity. Also, okay, so notice that case 1 is uninteresting in the sense that it is a trivial case where f is identically 0. Okay. Poles and zeros, okay, fall into case 2. What I mean by that is, if f has a 0 or if f has a pole, okay, then case 2 holds. Okay. Even if it has a removable singularity, then case 2 holds. Okay. So, we saw that. Okay. So, there is an integral divide. In the case of poles, the divide is at the integer which is the order of the pole, okay, and in the case of zeros, the divide is at the 0, the order of the 0 at A. Okay. In the case of removable singularity, well, it depends on the limit as z goes to A of f of z. Okay. So, limit z goes to A f of z could be 0, which will actually then give us a case where the order of the 0 will matter. If the limit z goes to A f of z is non-zero, okay, then the divide, the integral divide is really at h equals 0. Okay. So, removable singularities and poles, okay, and zeros fall in case 2. Okay. And then everything else in some sense, everything else is case 3. If neither 1 nor 2 holds, then we have what is called an essential singularity. Okay. So, we will see more about the behavior of a function which is analytic in a neighborhood of A, and it has an isolated essential singularity at A further. Okay. So, we will particularly state and prove the Casorati-Weierstrass theorem.